Okay, let's just start. So first one is from like the 0th question. So 2 exercises in textbook. So first one is so this is 12.1 from the textbook. So yeah, I'm guessing the question was asking if you have 3 particles and you have 3 non-degenerate energy states, or like, in fact, it doesn't even have to be energy states, it's just 3 states, some kind of quantum states. And for 3 parts, they ask how many ways can you arrange these particles in these 3 states, given that for part A, they're fermions, for part B, they're bosons, and for part C, they are classical particles. So for part A, it's the easiest one. So if they're fermions, quantum particles, they're indistinguishable. So if I showed you one of these 3 particles, you wouldn't be able to tell them apart from the other one. So fermions, they obey the Pauli exclusion principle. So in a non-degenerate state, you can't actually put 2 of them in the same state. So that means you have 3 particles to 3 states. One has to live in one each. So state 1 has a particle, state 2 has a particle, and state 3 has a particle. And since I can't tell any of them apart, this is essentially the only configuration that I could put them in. So there's only one way to arrange them. Yeah, so fermions are usually easy because they can't stack on top of each other, so they generally stay away from each other and social distance before it was cool. Okay, a bit harder is bosons, because for part B, when you talk about bosons, they're still indistinguishable, but this time they're able to kind of live in the same state. So configurations like all 3 bosons in the first state and none in the second, this is now allowed. So now we have a couple of cases to consider. So the easiest one is these kind of states. So I have 3 distinguishable non-degenerate states. So we can call them like, say, like, I don't know, epsilon, 2 epsilon, 3 epsilon, if it helps you visualize it. So since they're bosons, you can, the first case is that, let's do it here. So case 1, 3 in one state. So they all get stacked on top of each other. And obviously, there's only 3 ways to do this. You stack them in the first state, or the second state, or the third state. So that gives us 3 ways. And okay, nothing fancy there. You just basically treat them as one fat particle to put them in like one of the 3 states available. Case 2 is you have 1 in each state. So again, like fermions, they're indistinguishable. So if you put 1 in each state, then there's only one way to do it. Oh, I mean, like you can do it several different ways, but you can't tell. So like effectively, you have one way to do it. And then the last case, case 3, is if you have 2 in one state and 1 in another, and 1 empty state. So for this one, since you put 2 particles into one state and 1 particle in another state, you can think about this as if this is effectively saying you have 2 distinguishable particles. So the question becomes, how do you put 2 distinguishable particles into 3 states? Because 1 is fat, you can imagine 1 is like double the size of the other. So you're saying like, okay, I have a fat particle and a skinny particle, and I have 3 states to put them in. So now I have 2 distinguishable particles into 3 states. So in that case, I always forget how to do this. Okay, so this is like, I don't know, high school combinatorics. So you start with the first particle, whether it's fat or skinny, you have 3 options to put in the first particle. And after you chose a position for the first particle, there's only 2 options left for the second particle because they can't all go in the same place. Yeah. Okay. So then that gives me 6 ways to do that. I don't have to consider internal switching between the two in one state because they're indistinguishable. So then I don't have to worry about how which one of these two is the fat or skinny particle. So altogether, there's only 6 ways to place them. So in total, adding all this together, for bosons, 3 bosons in 3 states, we have 10 ways of arranging them. If this gets larger than 3, you probably want to look up the generalized formula because this will take you forever to try to reason through in general. Okay, and the last one, part C, is the distinguishable classical particles. Okay, so part C is that they're classical, which means they are distinguishable. So you have 3 particles, you can label them A, B, C, and they go into 3 states that you can distinguish. So this is, again, quite easy because since you can distinguish them, then you can treat them individually as saying how many choices do you have. Each particle has 3 choices, and there's 3 particles to go through, so they're just 3 times 3, 3 to the power 3. Yeah, so each particle has 3 choices. So the first one has 3 choices to go which one of the states. Second one has 3 choices. Third one has 3 choices. So altogether, you have 27 unique configurations. Yep. All good? Cool. Am I actually recording? Yes. Okay, good. Okay, so there it is a combinatorics exercise. Yes, yeah. We'll show later that when you derive the entropy formula, they differ by a sign because of that. And with as temperature scales, they scale differently. Okay, so 12.2 from the textbook. So it's asking you have 2 particles. They are quantum particles, they're indistinguishable, and you have 3 states available. And these are energy states, whether it's the ground state 0 energy, or epsilon, or 3 epsilon. And is asking you to find the partition function, find Z. If for case A, they're fermions. So you basically want to find the total energy possible. Because Z in this case will be given by like the sum of all the minus beta epsilon, maybe abuse of notation here, let's just call it E for energy to distinguish between the actual energy, the energy states. So I just need to find all the possible energy states for this total 2 particle configuration. And fermions, again, the 3 states assume they're non-degenerate. So that means you can't put 2 in one state. So if you imagine the first particle is in the 0 energy state, then the second particle has to be in one of these 2. So that means my total energy could be epsilon or 3 epsilon. If one of my particles in the epsilon state, the other particle could be either in the 0 state, in which case I have epsilon, but we already have that, so we won't count that again. Or we could have the 3 epsilon state. So now my total energy is epsilon plus 3 epsilon. So 4 epsilon is also possible. We can't get any higher because they can't both sit in the 3 epsilon state. So these are the 3 only possible combinations of total energy that's available. So in this case, our Z would just be e to the minus beta epsilon plus e to the minus 3 beta epsilon plus e to the minus 4 beta epsilon. And again, you don't have to, even the one epsilon state, you could have two different ways of arranging them because their fermions are indistinguishable, so you don't have to think about any degeneracy or like picking up extra factors here. Okay, and similarly for part B, you want to consider what happens if they are bosons. If the bosons are going to be more combinations because they technically are able to sit in the same state. So for example, zero energy is now possible because both of them can sit in a zero state. So zero is possible. If one of them stays at zero, you can go up. So one's epsilon, 3 epsilon, they're all possible. Epsilon, 3 epsilon. Both of them can sit in the 1 epsilon state. So 2 epsilon is also possible. And then there's also 4 epsilon and also 6 epsilon. You can't have 5 because you don't have 2 epsilon. And yeah, that's the highest you can go. So this is Z is just going to be, okay, e to the 0, so you get a 1 plus e to the minus beta epsilon plus e to the minus 2 beta epsilon plus blah, blah, blah. You know the drill. So minus 6 beta epsilon. Okay, I guess I only saved one term here. No, I saved 2. Okay, I'm not going to bother writing it out. Yeah, just all of these energies in the partition function, and you got for the ensemble here. Yeah.
Instead of like that, 3 states, you had 0, 2, and 4.
Yeah.
Would that mean that you could get a degeneracy on 4 energy? If you have 0, 4, and 2 twos.
Yes. Yeah. That would mean you can double up.
And then the 2 outside the expansion.
Yeah, that's right. Cool. Yeah, these are simple exercises. I guess that's why the question is 0, because they're technically like simple counting exercises. And since this course is not on combinatorics, they probably won't get any weirder than this. Okay, so question 1. You have a paramagnetic system. So suppose you have a system of question 1. You have n identical particles, and they're localized, so they're not moving or interacting, and they're freely orientatable magnetic dipoles. So the only energy we need to consider is the potential energy of the dipole in a magnetic field. And they give you the energy term. So here is minus mu b sum from the first particle to the nth particles over all particles of cos theta I. So in this case, this cos theta b is the, like, you can think of it as a projection of the magnetic moment onto the z-axis. And they could be, each one of them could be pointing in a different direction depending on which particle it is. So they're not guaranteed to be the same. And we have to do a whole bunch of things. So for the first one, we have to find the expression for the canonical partition function of the system in terms of the single dipole partition function. So let's do it for a single particle or a single dipole. Oh. This is question 1, part 1. Okay, for a single dipole, Z1 is just going to be the exponential of, it's going to be proportional to, so it's going to be exponential to the minus beta epsilon, not epsilon, E, so let's call it H1. So this could be like a total Hamiltonian. But this one, I only have the individual one dipole Hamiltonian. And if I have if you consider the total Hamiltonian of the entire system, is just going to be the sum of all the individual Hamiltonians. And you will never get a term that's like a mixing between, like, say, the first and second dipole, because they're non-interacting. And so if you consider the total partition function for this entire system is going to be proportional to e to the minus beta h total. And this would just be the sum of all this. So if you imagine that in the exponential, this would just be equal to e to the minus beta h1, e to the minus beta h2, multiply all with e to the minus beta hn, goes on, like that. And since each dipole is technically identical, then these Hamiltonians going to be on average the same. So this would just equal to a single dipole partition function to the power of n, which is quite common, a quite common result for non-interacting systems. If you have n identical particles, your total partition function can be found by just getting the n copies of the individual particles partition function and multiplying them together. If they have interaction terms though, then this is not true, because then you're gonna pick up like extra terms in there that doesn't factor out very nicely. Okay, and moving on, the next part is to find an integral expression for the single dipole partition function of the system. So for a single dipole partition function, you have z is equal to basically this, except you don't have the summation, you just have like one angle. So here you have e to the minus beta mu b, the two minus signs cancel out as plus, beta mu b cos theta. And I'll drop the I because it doesn't really matter. And what we have to do is to integrate this over all possible orientations. So in this case, we can go from 0 to 2 pi or 0 to pi for both the d theta and d phi. And because of spherical coordinates, we pick up an additional sin theta in the Jacobian. We don't have to integrate over the radial part because we're assuming it's like a fixed radius length mu dipole. So all we have to care about is integrating over the possible orientations it could take and not the actual length of it. Okay, so looking through this expression, okay, get rid of this plus sign. You have just the theta dependence. So the phi integral kind of just trivially evaluates itself. So just be 2 pi integral of e to the beta mu b cos theta sin theta d theta from 0 to pi. And you can do a simple substitution where u equals cos theta du equals minus sin theta d theta. And your integration limits when u is equal to 0, when theta is equal to 0, u is equal to 1, theta is equal to pi, u is equal to -1. So it goes from 1 to -1. So we can flip that integration limit back around by canceling out this minus sign. So this integral ends up being 2 pi -1 to 1 of e to the beta mu u du. And once you do that integral, I already forgot what I did. Right, it turns into like 2 pi divided by beta mu b. There's a b in here still. Beta mu b, and then inside you have e to the beta mu b minus e to the minus beta mu b. So this thing is 2 times the sine function or the hyperbolic sine function. So in total, your partition function is 4 pi beta mu b hyperbolic sine of beta mu b. And that's a partition function for a single dipole. Okay, now that we have the partition function for one of them, part 3, find the expression for the mean magnetic moment of the system in terms of the partial derivatives of a single dipole partition function. Okay, so part 3, you want to find the mean magnetic moment, which is just another way of saying like you have, for each one you have mu cos theta of magnetic moment contributing from each dipole. If I have all n of them together, then I'll just have like a factor of n out the front. And since they all have different orientations, I'll have to like average over the cos theta. They all have the same mu. They just have different orientations. So I only have to average over cos theta and not the mu. So this is what we call the mean magnetic moment. So call this mz is equal to that. Okay, so this in general, if you don't know better, to get this average, you'll just do it like I normally would. So m mu and then times the integrating over all the possible orientations of cos theta weighted by the probability. So p beta mu b cos theta sine theta d theta d phi. And then normalized by a partition function, which is just e to the beta mu b cos theta sine theta d theta d phi. So this is a general definition for just averaging over some quantity that weighted in your probability space. But in this case, we don't have to, we can simplify it because the bottom part, like we said, is just a partition function. We know that. So m mu on z. This thing, if you look at it, it's just the derivative of the partition function with respect to the magnetic field. And then you pick up some additional factors at the front. Yeah, you pick up a 1 over you pick up 1 over mu beta out the front. Yeah. So if you have this partition function, it's integrating over theta and phi. So if I take a derivative with respect to b, it doesn't actually affect this integral at all. I'll just pull down a factor of cos theta with some constants at the front, a mu and a beta. So now I cancel that out with that. So I can rewrite this whole complicated expression just like that. And the mu's cancel out. So I end up getting n over beta of d log z d beta, db, so not beta. So that's what you basically have to do. So there's the mean magnetic moment written as a function of the one dipole partition function. If you have to take averages like this, these variables are usually related to your energy or partition function somehow. So if you see something like that, generally what happens is you just go into a partition function and look for that variable and see what you have to differentiate with respect to. And it generally works out this way. Okay, and for part 4, you just have to evaluate what you found in part 3. So we just have to carry out this derivative, and we're subbing in the z that we found in part 2. So for 4, we'll just be doing d log d dB of the log of 4 pi on beta mu b, hyperbolic sine of beta mu b. And yeah, okay, this is a slightly ugly derivative. You got 2 terms because you got 2 magnetic field dependencies in here, but it's not impossible, and it eventually looks like mu hyperbolic tangent, hyperbolic cotangent of beta mu b minus 1 over beta mu b. So you basically do the first term, you end up with the second term, and then you do this term, you get a hyperbolic cosine, but then because of the log, you have to first pick out like 1 over this entire thing. So hyperbolic cosine and the hyperbolic sine in the denominator makes this hyperbolic cotangent. And the constants should all cancel each other out fairly nicely. So you don't have to carry those around. But yeah, like it's just math. And yeah, this thing has a special name. It looks like a curly L. So this is the Langevin function. Sorry if I butchered the pronunciation. I don't really know how to say it. It's the some math function. And yeah, you can plot this out and it will look something like this is this axis is beta mu b. So if you plot this thing out, it looks something like that and it approaches 1. Yeah, and I think if you change mu, you just change like how it approaches 1, like could get steeper and then like that. So for different mu values, you just change the how quickly it approaches 1.
What is on the y-axis?
Y-axis is your average magnetic moment mz. Okay. Okay, and for part 4, that's what we did. Part 5, if you have n or dipoles per unit volume, the mean magnetic moment per unit volume n naught, m0 naught will be given by, okay, so you define some like your magnetic moment but per unit volume. So that's given to you by some n naught mu times the Langevin function and as a function of beta mu b. Or they introduce a new variable eta in there, but like it's just beta mu b. For high temperature or equivalently weak magnetic field, so weak magnetic field means that beta mu b is much less than 1. So this function is very small. This variable is very small. Find the susceptibility. We have to find chi, which is given by the limit of the auxiliary field going to 0 of how the magnetic moment changes with the auxiliary field. A very condensed matter question. Okay, so the main point here, just like here, we're saying that we have a small variable and we know what the Langevin function was. So if you just expand L of beta mu b, like around a small beta mu b. So Taylor expand this. You can go back to the cotangent and all that to try expanding it. I think if you can just look up the Taylor expansion for the Langevin function, and it tells you that the Langevin function when expanded out is just the variable divided by 3 for a small variable. So in that case, we know what the total magnetic dipole mz for all of them are. But in this case, we want the magnetic dipole, the magnetic moment per unit volume. So you have to divide by v to get the mz 0. So in this case, if we put in our previous answer for mz that we got above there, then we get mu n on v times by the Langevin function but then we're expanding it around a small magnetic field. So this would just be replaced by beta mu B on 3. Yeah, so in this case, this thing will end up as n divided by V. So that's just the number density in the volume. So it'd just be the little n 0. That's the number density per unit volume. Times by mu squared B divided by 3 kT. So I re-express beta in terms of K times T. And okay, this thing can then be, again, rewritten because we want to ultimately take, so this is NZ0. We want to take the derivative of this with respect to the auxiliary field. But right now we're having it in terms of like the physical B field. So we assume the weak field limit and then, actually we already assumed the weak field limit. So we can then substitute this B for mu naught H. So this will be N naught, mu squared, careful they don't say mu, times by H divided by 3 kT. So here we just sub B equals mu naught H. And now we have a function of mz0 in terms of the auxiliary field. We can then find the susceptibility by just differentiating this. So chi in this case is just limit of H going to 0 of the derivative of this. So just m naught mu squared on 3 kT. And it doesn't even depend on H. So this limit is completely trivial. So this just equals n naught mu squared 3 kT. I may have forgotten the fact. Oh, no, I didn't. Okay. There's a factor n in there. Okay, that's good. Okay. Get that back down. All right, so for part 6, you have to then find the heat capacity per dipole. So to find the heat capacity per dipole, you look at the definition for heat capacity. So heat capacity, let's see, H is the internal energy per dipole dt. So in this case, we're going to first find out what this average internal energy is. So average U in this case will be given by the average magnetic moment times by the magnetic field. I think that's by definition the energy of a dipole in a magnetic field. So in this case, this thing I have I don't know why we switch notations here, but this is essentially the average dipole moment per particle, per dipole. Doesn't matter which you choose. So if you look back at what we got before, we had the total magnetic dipole moment. And if I just want to do per particle, I just have to divide by n. So mu bar is essentially identical to this expression. And yeah, if we sub in the expression for mz, then we just have mu n times by the lengthening function divided by n. So the n's cancel out. So what I have left is just mu times the lengthening function. So that's the average magnetic dipole per particle. rather than the average of the entire ensemble magnetic dipole. Okay, so yeah, now that we got this and we know what the Lambing function is, we can just easily put it back into here. So this whole thing is just equal to minus mu b hyperbolic cotangent mu b on kt minus kt on mu b. Looks a little bit different because I wrote kt explicitly instead of the beta, but it's the same thing as before. Yeah, okay, and that's it. And all you have to do to find the heat capacity now is just differentiate that. So after you differentiate du1 with respect to t, then you get minus mu squared b squared on kt minus 1 plus hyperbolic cotangent squared of mu b on kt and then plus k. Again, it's just annoying algebra, but it's pretty straightforward.
My basic question.
Yeah, go ahead. Yeah.
So when we're looking for capacity, like this one we use du over dt, but so are we assuming for magnetic, like for this kind of system, there's no work done? So when we say heat capacity, it's CH, and we don't know that, we don't write it as CB or something like that.
Yeah, so because of the magnetic system, you know you don't change, you're not compressing or anything like that. Right. You're changing the energy by like applying an external auxiliary field to magnetize it or demagnetize it. Yeah. Oops. Okay, question 2. Very similar question. Actually, most questions at this point in the course is pretty similar. They all just fit around with the partition function. Okay, question 2, you have a semi-classical harmonic oscillator. So you just consider n independent oscillators. Yeah, they're just oscillators. And assume that the oscillators are one-dimensional, so the Hamiltonian is exactly what you normally would expect. So since they're independent, you would just be summing up all the individual energies from each oscillator rather than any interaction terms. So you got your usual kinetic energy term, the momentum squared, and then you got your potential energy term, and omega squared, qi squared. So Q here is just what you normally would see as like X, but as a canonical coordinates, writing as P and Q for historical reasons. And yeah, part 1, find the expression for the single oscillator partition function of the system. So, okay, since it's semi-classical, remember last time we said your partition function is proportional to some power of the Planck's constant. Since this is one-dimensional, we just get 1 power of h. Last time we did 2-dimensional problem, we had h squared, but here's just h. Yep, and then we just have to integrate over or sum over all of integrate over all of the possible momentum and possible position, so the entire phase space. So in this case, you'll get integrate from -infinity to infinity for both the momentum and position of e to the minus beta h dq dp. And luckily for us, the 2 bits are completely separate. So your p bit and q bit are 2 separate terms. So I could essentially separate this integral to do them one at a time. So I got 1 on h -infinity to infinity of the p bit. So e to the minus beta on 2m p squared dp times by minus infinity to infinity e to the minus beta on 2m omega squared q squared dq. So I can completely separate out the exponential for this. And both of them are just Gaussian integrals. They're integral in the integration over all of the real line for a squared exponential. So this is just a standard result that you can quote. So this will just be equal to 1 over h square root of pi over the prefactor of this thing. So it's over 2m on beta for the first one, and then square root of pi over all of those things. So 2 pi over beta m omega squared. And then collect the like terms and you end up getting 1 over beta h bar omega. And that should look relatively familiar as a harmonic oscillator. It's like ground state energy. You got your KT, the thermal bit, and then you got h bar omega for the quantum bit. Okay, now that part 2 asks to find the mean oscillator energy and the heat capacity per oscillator. So for the mean energy du, average U, you can find it from the standard formula d log z d beta. So I think you proved that in the lectures. So okay, in this case, Z, just take from what we got before. So this is just minus d log 1 over beta h bar omega d omega. Sorry, d beta. All right, and this integral turns out pretty simple. So you get the minus sign can cancel out by flipping this logarithm to the top rather than having 1 over. And then once you integrate that, you get 1 over h bar omega. 1 over beta h bar omega times by h bar omega. So overall, you just get 1 over beta or equal to KT. So that makes sense. Your average thermal energy is given by like your thermal energy. And to find the heat capacity here, CV is du dt. So just be equal to K. And that makes sense, right? Because if you remember the equipartition theorem, what this tells us that is we have F equals 2 degrees of freedom. And we integrated over 2 coordinates for the partition function, so we only had 2 degrees of freedom. So this result matches exactly what we started out assuming there's only 2 degrees of freedom. Yep, and well, CV is the same, like is the derivative of that, so that's fine. And for part 4, it's saying, okay, at high temperatures, diatomic molecules can be considered as particles with internal oscillator degrees of freedom. What would you expect the heat capacity of a gas of diatomic molecules? I don't really get why this question is even there because it seems to be entirely trivial. So it's basically saying at high energies, your normal diatomic molecules have 3 degrees of freedom in translation. So that means your internal energy is equal to 5 half, wait, 3 half. Wait, is it 3 or 5? It's F plus 2, right? Yeah, it's F plus 2, that's fine. KT. But then because we put it at high enough temperature that you get to like add the oscillator degrees of freedom in there. So you just add whatever we found here onto the end, which is equivalent to saying, like, proving explicitly when we say a high energy is when you unlock the oscillatory degrees of freedom, you pick up 2 degrees. So here is like an explicit proof why you pick up 2 more degrees of freedom. So now you get 7.5 kT. But that's pretty much it. It's just kind of recognizing that these are exactly the same thing as when we talk about it in equipartition theory. Okay, yeah, let's go about time. All good so far with everything? Okay, then next is also from textbook, so 12.3. Okay, so what I think the book is asking in this case, 12.3 is that to find in a grand canonical ensemble, find the entropy for both Fermi-Dirac and Bose-Einstein distributions. So again, in a grand canonical ensemble, you can start off by just saying the log partition function is given by the sum over the log of 1 plus or minus here, e to the beta mu minus epsilon. So in this case, plus corresponds to Fermi-Dirac and minus corresponds to Bose-Einstein. So this is plus, minus. And as usual, you can have your grand potential as well. Omega g is minus kt log of z. And to find, so recall from like early on in thermodynamics where you like shown that the grand potential is basically a Legendre transform of energy. So you get plus s dt minus n d mu minus pdv. So if I want to find the entropy, I can find it by taking the derivative of the grand potential with respect to temperature, holding mu and v fixed. And if we have this definition of grand potential, and in turn putting this in there, then we can work out an explicit formula in terms of the energy and chemical potential on what the entropy is going to be. So from this point on, it's just chasing a whole lot of algebra. Not that much, not that bad. Okay, so then let's just do the derivative. So rather than doing d omega g dt, or minus d omega g dt, we see that beta is a bit more like easy to work with. We don't want to expand it out and get a bunch of 1-on-t's. So we just do a change of variable to turn this into k beta squared d omega g d beta. So this is still the entropy, but now I get to cheat again and do it with respect to beta instead of t. Okay, so now to evaluate d omega g d beta, this will be taking the definition from before. So plus or minus 1 over beta squared sum over r log of 1 plus or minus e to the beta mu minus epsilon r minus 1 on beta sum over r Okay, so all of this thing. Yeah, again, you got two terms because you end up using the product rule for it. Yeah. Okay. So yeah, this looks really ugly, and then you can slightly simple. Okay, so writing out for the actual entropy. So adding these two prefactors in there, and then cleaning up this bit a little bit. So we get the entropy is equal to plus or minus k, so the beta squares cancel out with the beta squares here. And we have sum still over log 1 plus or minus e to the and then this part plus k. So we've cancelled out this minus sign here. Beta epsilon r minus mu divided by e to the beta epsilon r minus mu plus or minus 1. So yeah, put a little sneaky here. So I basically divided out by this exponential up here and then canceled out with this one. So that's why this one ended up on the front. So it's now epsilon beta epsilon e to the beta epsilon r minus mu plus minus 1 rather than the other way around. And yeah, this part's still fine. So what you should recognize now is this piece here, the 1 over epsilon e to the beta plus or minus 1. This is the distribution function. So this is the average occupation number. So plus will mean Fermi-Dirac and minus will be Bose-Einstein. So FD or BE. So you basically worked the distribution, the occupation function into the entropy formula. And you can do the same trick over here, where you take the minus sign to invert the log to get a 1 over this, and then get it into a similar form like that to basically, okay, I'll just write it out explicitly. Here, minus log of 1 over 1 plus or minus e to the beta mu minus epsilon r is equal to minus log e to the beta epsilon r minus mu divided by e to the beta epsilon r minus mu plus or minus 1. So yeah, pretty much did the same thing as that one, except this time I multiplied both top and bottom by e to beta epsilon r minus mu. So then break this log into 2. You end up getting one of them where the log and the exponential just cancel each other out, and you just get beta of mu minus epsilon r. And the second term is just the denominator, just 1 over this, and that's the distribution function. So that's minus log of the average n. So then overall, your entropy could be written entirely in terms of the occupation number. So S will then equal, with both of these put into that, you get S is equal to plus or minus K sum over R of beta mu minus epsilon R minus log of average n minus K Yeah, so this final line is the entropy expression. And again, yeah, this plus or minus sign here is determined by the, sorry, close the bracket, by the Fermi-Dirac or Bose-Einstein. So like I said before, depending on which distribution you take, you're going to get a different entropy at different temperature. Yeah, okay, and 12.4 is pretty much going through this exact same process. They did it via the Helmholtz function instead of the grand potential instead, and you're doing it for a classical Maxwell-Boltzmann distribution rather than a Fermi-Dirac or Bose-Einstein. But the process is exactly the same. You find the grand potential or find a Helmholtz function, and then find the relationship between entropy and the Helmholtz function, and then just going through all these algebra. And yeah, I'll leave that for you as an exercise. Cool, and that's it for today.